There we are. Okay, thank you very much everyone for soldiering on till the bitter end. I know it's been a long day. I'll try to be brief. So what I wanted to talk about today is implementing vaccination during a foot and mouth outbreak, but in the presence of uncertainty, because as we know, there are huge amounts of uncertainty during an outbreak in terms of how effective vaccination is going to be. Really, this is focused on the idea, when we're in the middle of an outbreak, really, we're so focused upon analysing the dynamics of that outbreak that it's very difficult to look in detail as to how effective vaccination is going to be. However, in peacetime, we're in a position where we can try to increase our knowledge and reduce uncertainty, so we're better prepared for the next outbreak to come along. And we know, and certainly my experience from the UK in previous outbreaks, is emergency foot and mouth disease is very contentious, and part of this issue with it is because of the uncertainty in how effective vaccination is going to be during an outbreak. So what we really want to think about is how do we deal with this uncertainty when we're trying to make predictions regarding how we should implement vaccination. And I'm going to focus on three aspects of vaccine uncertainty in this talk. I realise there are probably many more. For instance, the first one really is, how effective is the vaccine? What's the time delay between vaccination and the livestock becoming immune? And how many cattle do we have the capacity to vaccinate each day as part of an emergency response? Now, you've seen a lot of modelling talks in this session, and probably every single model will have a different prediction of all of these quantities that will be made for very good reasons, but in reality we know, actually, there's a huge uncertainty, and it's very variable between countries. So during the 2001 outbreak, vaccination was on the table as a potential control measure, and throughout the epidemic we were continually asked about whether we should vaccinate. And probably the key question was, if we did vaccinate, what size of ring should we use? And what we're interested in is how do we determine that when we don't know what the efficacy is, we don't know what the capacity is, and we don't know what the time delay is. So, for instance, just to give you a toy, let's say this is the vaccine efficacy of a herd, and we know it's somewhere between 0% and 100%. Well, if it was there, if it was 0%, then clearly you don't vaccinate because it's not going to do anything. If it's 100%, then you're probably pretty sure that vaccination is going to be good, so in that case you probably are going to vaccinate. But if it's somewhere in the middle, maybe actually you might want to vaccinate, but you're not quite sure. And if you decide to vaccinate at 50%, you probably want to do large vaccination rings because you know the efficacy is not high. But if it's 100%, you might be able to afford the rings to be smaller because you know that you're getting really good coverage. However, in reality, there is some range of uncertainty in what the vaccine efficacy is. And in that case, we need to know, given we have uncertainty, should we vaccinate? And if so, what size ring should we use? And to highlight this, I'm going to present in this talk really a toy example, just to highlight how we might focus in on the optimal vaccination strategy in the presence of this uncertainty. So, excuse me, I mean, as the modeler, you're going to get some assumptions, and excuse me for the validity of these assumptions. Let's say we know that vaccine efficacy is either 50%, 70%, or 90%. In reality, of course, it's a continuum of uncertainty. This is very much a toy. Let's say we know the time delay to immunity is either 2, 4, or 6 days. And let's say that we know we have the capacity to vaccinate either 20,000 animals a day, 35,000, or 50,000. I said this is a toy. And the policymakers are considering 5 possible radii of vaccination: 3 kilometres, 5, 7, 10, or 15. So based on this information, we want to determine what the best thing to do is. So this is the only equation in my model, and I'm going to skate over it really quickly, so don't worry. This is, we're using the Warwick model, which is it's a model that was used during the 2001 foot and mouth outbreak. I'm only showing you this so it doesn't look like a black box. I realise showing this to some members, it might still look like a black box to some people in the audience. But it's based on factors such as how susceptible the livestock are, how many animals there are on a farm, how transmissible the livestock are, and this final parameter, which is a transmission kernel, which essentially rates the risk of infection based upon distance between susceptible and infected farms. So it kind of looks something like that. So it's sort of common sense. The closer you are to the source of infection, you've got a higher risk of infecting and decreasing outwards. Now, all of these parameters can be estimated by fitting to the 2001 epidemic. And I realise that's a whole other talk there, just skated over in 20 seconds. Now, what we could do is just use the brute force modelling technique, and we'd say, right, we're going to run every possible scenario, we're going to run all the vaccine efficacies, we're going to run all the time delays, and we're going to run all the capacities, and all the vaccination radii. And we can get this grid. So, where we have vaccine efficacy, capacity, and time delay. And these are the vaccination radii along the bottom. And each one of these values in the grid gives you a cost of that particular control measure given the assumptions regarding vaccination. So, for instance, that element there says if we vaccinate 10 kilometres and we know the efficacy is 90%, there's a 6-day delay and 50,000 doses per day, that's the average number of cattle that will be killed. So, and so on for the rest of the grid. So if we look at this grid, there's a certain number of trends that we can pick out. So if we see, just looking at varying time delay from 2 to 4 to 6 days. Sorry, the other thing I should say is the lighter the colour, the lower the cost. So really looking for the more yellow ones. So as we vary the time delay, actually what is the optimal strategy appears to be completely unchanged. So the optimal strategy appears to be independent of the time delay to immunity. However, as we increase the capacity, i.e. the number of animals we can vaccinate per day, we see this trend for increasing vaccination radii. I mean, I realise this is very much common sense. If you can vaccinate more animals, you can afford to have bigger rings. I'm not inventing something incredible here. However, if we have uncertainty in vaccine capacity, then we can determine what the best strategy to do is. So, I realise this is complicated, so what I'm going to explain is, if we know a priori how many doses we've got, we can always determine the optimal strategy. So, just to explain this triangle, that point on the triangle says if you're 100% sure that you've got 20,000 doses, then you should vaccinate at 5 kilometres. That point says if you're 100% sure that you've got 50,000 doses, you should vaccinate 15 kilometres. And then if you change your belief through the triangle, a different strategy becomes optimal. So based on belief, you can determine what the best thing to do is. But if we then look at uncertainty in time delay and vaccine efficacy, we see something really interesting, that this, as we change the belief in both the time delay to immunity and the efficacy, it doesn't affect the optimal vaccination radius if we're considering what minimises the outbreak duration. But in this context, 15-kilometre vaccination is always the best thing to do if you don't know what your outbreak duration is. Oh, there's a problem with my virus. There we are, sorted. So this is really interesting that actually uncertainty in time delay and vaccine efficacy doesn't really affect what I would do if I want to minimise the duration. Now, if I'm more interested in minimising livestock culls, I see a similar effect in that there is some information to be gained between maybe 7 and 10 kilometres if I don't know what the delay to immunity is, and some with vaccine efficacy, but the vast majority of information is in resolving vaccine capacity. So what are the savings we can make? Just summarising this, if we can resolve all uncertainty. So if we just look at livestock cull, if we were able to resolve all uncertainty in how vaccination worked, then according to this model, then on average, I would save about 200,000 fewer livestock in an outbreak in the UK, which is round about 5 to 10% of the overall outbreak size. So it's quite significant in terms of saving animals. However, if I knew the true vaccine delay, I'd only get 3% of that saving. If I knew the true efficacy, I would get 7% of that saving. But knowing the true capacity, I can actually make 90% of the saving of resolving uncertainty. And to me, this is really powerful because vaccine capacity is something as policymakers, the policymakers should be able to tell us. They should know how many people they can put in the field to do their vaccine. But it's less clear when you're looking at herd level what the time delay and the efficacy is. But this would imply that actually that is less crucial when it comes to determining the optimal strategy. So to conclude, I think I've shown there are potential savings to be made if we resolve capacity. But resolving uncertainty regarding effectiveness appears to be significantly less important. And hopefully, this can then allow for informed decisions to be made about what the vaccination radius is to use during an outbreak. Okay, hopefully that was relatively quick. I just ought to say this work has been done really by Naomi Bradbury, who's not here, and Will Probert, who is. They've done really, all the exciting work here. And thanks to my collaborators and funders. Okay, I'm done.
Thank you very much. Do you have some questions? So at the end, the UK should have vaccinated or not in 2001?
Should the UK vaccinate? That's a question I'm not going to answer. The other issue that we've not discussed, of course, if the decision to vaccinate obviously affects exports, which is the major issue, that as soon as you decide to vaccinate, all of a sudden you're adding months to your length of your export ban because of getting the vaccinated animals out of the population. And so, we can only really advise, should you decide to vaccinate, what's the optimal strategy? It's much more difficult to decide, obviously, whether you should vaccinate in the first place, because there's a lot of political repercussions to doing that.
Okay. One question? No? Okay, so thank you very much again. Thank you. And
well, thank you to all our speakers again.